Hello.
Hello. Hi, how are you?
I'm okay.
Are you able to see my screen?
Yes.
Okay, excellent. So it just looks like a white screen, that's it?
Yes.
All right. So how are you doing today?
Okay.
Okay. So your mother sent me module 3,
Yes.
and do you have the questions in front of you, or you want me to get them somehow onto the screen?
I do have them nearby. Yes.
Okay. So would you like to look at the Daredevil disaster question?
Yes.
That one's a pretty tough one, isn't it?
Let me see here. Yeah, that was. Yeah, that is a tough one.
Okay, so were there any parts of this question that you found to be especially difficult?
Uh, I guess just the core of like having to account for having to account for centripetal acceleration and gravity.
At the same time?
Yeah.
Okay, so in part 4A, did you have any problem with this free body diagram?
Uh, uh, okay, so I didn't. So okay, so it seems like you don't fully understand how we do this. It's kind of weird. So this is the first question, and I said this before, there's four people in a group,
Okay,
and I was actually only assigned the fourth question, not this one, so I didn't really get around to it like enough to work too much on it.
I see. Okay.
Yeah.
All right. So, well, we could work on it together then. I did this one last night. I did both 1 and 2 last night.
Okay.
So, so you haven't had a chance to look at this in a lot of detail yet?
No.
Okay, so the first question asks to do the free body diagram. So let me just get the pen working. I think that should work. Yeah. So we have, of course, gravity is the easy part, right? That's just mg.
Yeah.
And then the tension in the rope. So um, the rope is going towards this point P. So we have a tension force, which is going to be labeled by T. And then on the free body diagram, I think they asked also, it said include his acceleration vector and its components. So the acceleration, I'm going to change color here. So the acceleration, he's falling from here and he's falling in a circular path, right? So he's going to accelerate in this direction, right?
Uh, yeah.
So there's if we this is his path, and so we have an acceleration vector which is parallel to the path. His path is going this way, and then we also have an acceleration vector which is perpendicular to it because the in circular motion, just as you said, you were talking about centripetal motion. The force, the accelerating vector is going to go towards the center of the circle.
Okay.
So that's this A perpendicular.
All right.
So here in the solution, he used a squiggly line instead of using two different colors. But basically, the straight lines in this diagram are the forces, and the squiggly lines are the acceleration vectors. And in my case, it's the blue for the acceleration and the pink for the forces.
All right.
So this part is okay. Um, I hope that part is okay for you.
Yeah, just the A parallel just confuses me a bit. That's all.
Yeah, I get it. Okay. So in the question 4A, they say draw the free body diagram, and then it says include its acceleration vector and its components perpendicular and parallel to his path. So this, in this case, that's just his path. So the instructor put a dotted line to indicate the circular motion. So there's some circle. So there's some circular path that the daredevil is going to travel along. And at this point right here, the acceleration parallel to the path is going to be the blue vector.
All right.
So that's basically, it's a line tangent to the circle. Does that make sense?
Yeah, yeah.
Yeah, so if we had just a circle, and at this point on the circle, I'm going to change to blue again, that's the tangent to the circle. Do you know what I mean by tangent? That's like a calculus term, tangent.
Yeah, that I know.
Yeah, so at this point, the tangent is like that. At this point, the tangent is like that. So that's basically the path. That's where he's going. And so if you want the component of the acceleration vector, he's accelerating. He has a downward force acting on him and a inward force acting on him. So he's accelerating somewhere between these two vectors. He's going to be accelerating because there's going to be components from the gravity and components from the tension. So he's going to be accelerating somewhere. We're just drawing a line. The line could have been like this, or it could have been like that, or it could have been like that. We're just drawing it anywhere. And then we want to split up the acceleration vector into components that are parallel to the path. That means parallel to the tangent vector.
Yeah.
And perpendicular to the path. And perpendicular to the path will be the tension vector. The reason why the tension vector is perpendicular to the path is because the force acting on someone undergoing circular motion goes towards the center of the circle.
All right.
Yeah, that's a geometry matter, and I wish they taught it better in high school, actually.
The problem I have though is like I thought the velocity was only in that direction.
The velocity, yeah, so the velocity is in that direction of, so yeah, that's exactly true. The velocity is basically in the direction of his path, right? So the velocity is in the direction of A parallel.
All right.
And then we also have a component to the acceleration, which is going to go inward as well.
I see. Okay, so the acceleration parallel is like the same direction as the velocity.
Yeah, because they wanted you to, when they said parallel to his path. That's what it says in question 4A. It says include his acceleration vector. It has components perpendicular and parallel to his path. And so if his path is going this way, then the acceleration vector that is parallel to the path, we're going to take the acceleration vector. The acceleration vector actually goes somewhere. So I'm going to draw over here again. So I'm going to draw the gravity again and the tension again. And I'm going to say the acceleration is going to go somewhere between those two, right? Because the acceleration has some components coming from the gravity and some components coming from the tension.
All right.
Does that make sense? Like the gravity is pulling him down, but the tension in the rope is pulling him up.
Yeah, yeah.
So there is some acceleration vector, and now we want to split that vector up into two components. One of the components we want is the component that is perpendicular to his path, and that means literally along the tension vector. So this one is going to be the perpendicular.
Yeah, okay, yeah, that does make more sense.
Yeah, and then from there, we know that in circular motion, the inward vector is going to be perpendicular to the path. That's because these tangent vectors, they're perpendicular to the line going from the surface, from the circumference to the to the center. So these all these tangent vectors, the tangent vector over here will be perpendicular to the line going to the center. The tangent vector here will be perpendicular to the line going to the center. Does that make a bit more sense?
Yeah.
Okay, now I have to figure out how to get another page on this whiteboard. There must be a way to do that, right? Okay, I didn't want to erase everything, so. So have you used this Zoom whiteboard before?
Not Zoom whiteboard.
Okay. I'm just gonna ask someone to help. Okay, for now you you understand what's going on in this diagram. It's basically I've just repeated this diagram, but just drew it all over again so that I could explain the vectors more slowly.
Yeah.
So there's nothing new in this diagram compared to that one. So I'm going to erase this. And then we can start doing the problem. Do you know how to change? I'm just asking someone right now. Do you know how to get another page on this whiteboard?
Yeah.
Oh, I have to click that. All right. And then how do I get back? Okay, excellent. So I can switch between these two very easily. Excellent. Okay. All right, so then I don't have to worry as much about space. I can draw as large as I want. Okay, so they asked us to use conservation of total energy to determine the velocity as a function of the angle.
Let me just take a look again. Yeah, so it says use conservation of total energy to determine the velocity, the speed as a function of theta. So I meant speed, not velocity.
Yeah, excellent. So basically delta E, the change in total energy, that has to be 0 because of conservation of energy.
Yeah.
And delta E total, that equals delta kinetic plus delta potential.
Mm-hmm.
All right, so the kinetic energy, let me change color again. So the kinetic energy at the end, so delta K equals kinetic energy at the final stage minus the kinetic energy at the initial stage. The kinetic energy at the final stage, that is basically what we have, this mv squared, where the velocity depends on the angle. So depending on the angle between the rope and the horizontal, we have a different velocity.
All right.
And then we have minus half of mv squared of 0. At the beginning, the rope is parallel to the horizontal, so the angle is 0.
I see.
Am I going too fast?
No, it makes sense.
Okay. And it also says in the question that the daredevil starts at rest. So V equals 0 at the beginning, right?
Yeah, so the initial kinetic energy is 0.
Exactly, yeah. So now we have an equation for half mv squared. And then we also have to do the potential energy. How does that change? This one's a bit more complicated. So here I'm going to use, so here we have mgh, right? So it's mgh final minus mgh initial.
Yeah.
Okay, and the initial height, I'm going to draw that one in green again. So initial height is going to be h, right? Because they told us that the daredevil starts from a distance of h above the ground.
Yeah.
Oops, I'm moving the whole thing. Okay. And then, so to get the final h, do you think you know how to get the final h?
Well, if the final h is like at the very end of his trajectory, it would be 0, right?
Almost. So 0, h of 0 means that he's already hit the water. In this question, did you get a chance to read the whole question?
I guess I should reread it.
So this is the water. This is the height where he starts. And then he's going to undergo a circular path. That's not the best circle. Oops. You've had a chance to reread it?
Yeah.
Okay, so the reason the height is not 0 at the end is because he's going to, okay, the question says that he's going to undergo the circular path, and then at some point, the rope is no longer able to support the tension, so he drops parabolically. And then he hits the water on a parabolic path.
All right. So okay. So what would be the final height then? Would it be like would it be like an angle? Oh, maybe like maybe it's like H sine theta?
Exactly. Yeah. That's exactly right. Yeah. So when I started drawing this angle, then I think you got it perfectly. So it's actually H minus H sine theta, because what we have here, so the length of the rope is also H, right? The height, the length of the rope is H, and this height above the water where he starts is also H, right?
Yeah.
And this line right here, that is H sine theta, isn't it?
Yeah.
So if that's H sine theta and this is H,
Oh, yeah, we need the other part, which is H minus H sine theta.
yeah, so this distance will be H minus H sine theta, right?
Yeah.
So going back here, we have MGHF. That's going to be MG equals MG, and then the final height, not the final when he lands in the water, but the final for the purposes of calculating his total change in energy at some angle theta. That's going to be H minus H sine theta. That's his final height, right? So then
Right.
it would be minus MGH.
Yeah.
All right, so now we have change in kinetic energy is half mv squared. Change in potential energy is this mg times h minus h sine theta minus mgh. And we're going to say that delta k plus delta u equals 0. And then we're going to do what the question asked us to do, which is to solve for v.
All right.
Okay, so in the next page, then I'll write out the whole delta k plus delta u. That's going to be half mv squared of theta plus mg h minus h sine theta minus h, and that's equal to 0 because we want the delta E total to be 0, right?
Yep.
Okay, and then we want to solve for v of theta. So let's first just solve for v squared. We'll get v squared of theta equals, we can put all the other stuff on the other side, right? So this mgh is going to go on the other side. The mgh sine theta is going to go to the other side, mgh sine theta. And we're going to have minus mgh on the other side. And then we have to divide the whole thing by m, and we have to multiply the whole thing by 2.
Yeah.
Because we had half m there. Yeah. You're good at the math, so I don't have to spend too much time on the math part. So we have mgh and negative mgh, so we can remove those.
Oh, yeah, right. Yeah.
And then we just have mgh sine theta over m times 2. So we can remove the m's as well, I think. So we end up with 2 times gh sine theta. And v of theta will be the square root of that. 2gh.
Sorry, could you just give me a second? I have to write this down.
Yeah. Oh, you can get this copy of this after as well.
All right.
You can write it down. You can take screenshots, pictures, whatever you want. But I'm also going to give you a copy of this whiteboard at the end.
Yeah.
But yeah, you can write it down too if you want to follow along and try to do the same thing as me.
Then you square root. All right. Yeah. That's good.
Okay, so that's part of the question. They said that v of theta, in the solution, they said v of theta equals square root of 2gh times sine of theta. So we got the same thing as Richard Epp. But they also asked in part for to repeat the same calculation, but instead of using conservation of total energy, they want you to use the work kinetic energy theorem. So you know what that is?
Yeah. So the work kinetic energy theorem, I can't remember at the moment. It was like work is equal to, it was like kinetic energy, and then I don't know if it's just multiplied by displacement, but
okay. So that's force times displacement. That's the work. The definition of work is force times displacement. But the work kinetic energy theorem is saying that basically the change in kinetic energy is equal to the amount of work done. So the total work equals the change of kinetic energy.
Oh, now I remember that.
Yeah. So the change in kinetic energy we already have from here. So the delta K, that's half mv squared of theta. And now we want to calculate the work total because we want to calculate using the work kinetic energy theorem. We want to get the v of theta, and we want to find that it's the same as what we got using conservation of energy.
Yeah. Okay. So with the total work,
yeah,
I guess we just make that equal to other things.
Yeah. So the total work is composed of all the different types of work, right?
Yeah.
So what are the types of work?
Okay. So there Um, what exactly do you mean by that?
All right, so the total work is there's going to be some work due to the gravity and some work due to the tension in the rope, right?
Yeah.
So yeah, basically there's going to be some work due to the gravity and some work due to the tension in the rope. So that's what I meant by the two different types of work.
All right.
And then the definition of work due to gravity, that's going to be, now this is actually a very important part. I think this part, the solutions didn't explain it in enough detail. So I gave a lot more detail when I was writing this out yesterday. So the work due to the gravity, that's going to be the force due to the gravity dot producted with the change in position vector. So it's the force times the displacement.
Yeah.
And likewise, it's the same. This is just the definition of work. It's force times displacement. So we now have the force due to the tension in the rope dot producted with the displacement vector.
Yeah, because the simplest work formula is just force times displacement.
Exactly. Yeah, yeah. So now we can say force due to gravity is going to be, okay, well, first of all, we have some dot products here. So you know how to do the dot product in terms of the magnitudes of the vectors times the cos of the angle between them?
For dot product, I can't remember.
So if I have the force going this way and the displacement going that way, and I have an angle between them. Force times this. Do you know how to do that?
It seems familiar, but I don't remember exactly how to do it.
Okay, so this is going to be the force, the magnitude of the force vector times the magnitude of the position vector times the cosine of the angle between them.
Oh, all right. I see.
That's one of the ways to calculate the dot product.
Okay.
Okay, so yeah, sorry, I should have labeled these as RG and RT because this is the displacement due to, this is the work that the vertical force or the gravitational force does, and this is the force that the tension does. So in this case, let's write this out in terms of the dot products. So we have FG times delta RG times cos of the angle between them. And in this case, there is a vertical force, the gravitational force is going downwards. And so the gravitational force is going downwards and the tension force is going upwards and to the right. So 0% of the downwards force is due to tension. The only force vector which is going downwards is gravity.
Yeah.
So this is going to be causing the gravity, all the gravity does is cause the daredevil to fall downwards. So the tension in the rope is actually what's keeping the daredevil up, but the gravity is pulling him down, right?
Yeah.
The tension in the rope is not what's causing him to fall down. It's only gravity. So this angle is going to be 0 degrees because I have the displacement due to gravity is going to be parallel to the force due to gravity.
Yeah, because gravitational force is pointing down and the displacement or delta R is pointing down.
Precisely. Yeah, the displacement due to the gravity is pointing down. So we're going to have cos of 0 degrees there. And then for the other one, we have now for the other one 100% of the horizontal movement. So the fact that this daredevil is moving that way horizontally is 100% because of the tension in the force, because the tension in the rope, because the gravity is not causing him to move that way. Only the rope is.
Yep.
The rope being tied to this point, that's pulling him towards that point. So here we have the delta RT. I should write that neater. Delta RT times, I wish I had more space here. Okay, I'll be more careful this time. So delta RT times cos of 90 degrees. Because the force, this goes back to this diagram. So the displacement is going this way, and the tension is going perpendicular to it.
So it would be 90 degrees?
Exactly, yeah. So we have cos of 90 degrees there.
Got it. All right.
Okay, excellent. Now, do you know the cosine of 90 degrees?
Let me just think this out. I'm just doing it from memory. That would be 0, right?
Exactly, yeah, excellent. So this is 0 because that's 0. And you remember the cosine of 0 degrees?
It's 1, so it would just be gravitational force times delta RG.
Very good. And then the magnitude of the gravitational force, what's that going to be?
It would just be mg.
Okay, and how about the magnitude of the displacement vertically?
For that it would be would it just be h sine theta, or would it be h minus h sine theta?
Okay, so to answer that question, we're going to ask this time, we started over here and we want to know how much have we displaced vertically?
Oh yeah, okay, it is just h sine theta then.
Yeah, yeah. So that's what they wanted you to understand, because now we've done the calculation in two different ways. One of them uses the change in total energy, the conservation of total energy, which means we have h minus h sine theta. The other way we use the work kinetic energy theorem, which means we're talking about the work done. The vertical work done is h sine theta, not h minus h sine theta. So in one version of the problem, we used h minus h sine theta, and in the other version of the problem, we're using h sine theta. And in both cases, we're going to get the same thing because we're using the appropriate theorems, the work kinetic energy theorem versus the conservation of total energy theorem. So here now we have that the total work, which equals delta K, and delta K, we already calculated that before, that was half.
Oh, yeah, I'm just looking at, I'm just comparing it to the first method, and yeah, it's exactly as planned.
Yeah,
Because if you sub in a delta K now,
yeah,
it's just the same thing, because it
yeah,
divided by half, you get 2, divided by m goes away, square root, it's all the same.
exactly. Yeah, so the m's are gone, and then we just have 2g h sine theta, right? Yeah. So the point of the question was to show that the work kinetic energy theorem and the conservation of energy are both going to give the same result.
All right.
Now there's another part of the question, and it says how much work does the tension in the rope do? Did they even answer that part? How much work? So that part,
Well,
well, that part we already calculated, right?
yeah, wasn't it 0?
Yeah, yeah. So the gravity is doing all the work in this case. The tension is just stopping you from falling. It's just trying to keep you up. The gravity is doing all the work.
All right.
The tension isn't causing the change in kinetic energy. Okay, so good. You got that one right. And so we can go on to part B,
Yeah.
if you're okay with it. So for part B, it says use the V of theta that we just calculated to determine the tension in the rope as a function of theta. So do you have any idea how we would start that question?
Okay, so I'm just thinking it through. So tension is a force.
Yeah.
Uh, would we? Would we? Would we use like one of Newton's laws, like F equals ma, and then go from there, or am I overthinking this?
Good idea. Yeah. So we should start with talking about the forces for sure. So let's see what I wrote down here. So one of the things. So first of all, the total force. Yeah. So the force. The perpendicular force is going to be the tension plus whatever perpendicular force we're getting from the gravity. And I will draw that out for you. So here we have this tension in the rope, and we have the gravity. This is the tension in the rope. And then we have our coordinate system. We have a vector parallel to the motion, and the gravity is going to have some. This is perpendicular to the central force. So the gravity is going to have a little bit of a component in the direction of the motion, and also a little bit of a component in the direction perpendicular to the. So this is the parallel. We have the gravity has this one, which is, do you know what this is going to be?
Oh, let me think. So just trying to think where theta fits into this one right angle triangle. Okay, so it would theta be at the bottom or the top of that right angle triangle?
Okay, so the theta that they defined theta compared to the horizontal.
Wait, let me think. So I'm just thinking of like all those rules, like the Z rule, the F rule, those rules.
Exactly. Yeah, that's. I don't know if the F rule. Yeah, you could maybe use the F rule as well. You can definitely also use the Z rule.
Yeah. Yeah. Okay. I'm seeing the Z rule. So like where that right angle triangle is, like the bottom one.
Yeah.
Like up there. So sorry, it's hard to explain online.
This one over here?
No, up.
This one?
To the right and down.
This one?
Up there. From yeah, from there to the red dotted line, that's also theta.
Yeah, that's from the Z rule, right?
Yeah.
Yeah, okay. And then so to get this vector, we need this angle, right?
Yeah,
Okay, so how do you think we're going to get that?
I remember seeing. I'm trying to remember what could be used here. And I guess I shouldn't make another angle.
Well, I think it's maybe a good idea to make another angle. It's not a
Okay.
bad idea. So we could call this beta,
Yeah, okay, if that's the case,
and this one is going to be what?
then that would be beta, right?
Precisely, yeah. And then we have a right angle here. We have
Yeah,
a right angle there.
and then theta would be in that triangle. Okay, so the top angle would be theta.
Nice, yeah. So now you think you can get this component of the vector?
Yeah. So the component you're trying to find there
Mhm.
would be that would be that would be mg cos theta.
Precisely. And then we also want to get the component of the gravitational force in this direction. So that will be what?
Uh, that would the angle would well, I would like to use theta, not beta for this. So, oh, that would also be zero, right?
This component?
No, no, I'm thinking it would be mg sine theta.
Yeah, so mg sine theta, that's right. However, it's going to be in the negative direction compared to this, the coordinate system. If our coordinate system has this as its origin and this as the, do you know the right hand rule?
Uh, oh, the right hand rule. For not I know of a right hand rule, but not for something like this. I know it for like 3D things like
Yeah, yeah.
electronegativity.
Yeah. Actually, we don't need the right hand rule here. I'm just going to say that because we can define the coordinate system however we want. So if you wanted to define the positive j direction to be in that direction, that's up to you. But I'm just going to label this as I hat and j hat. So then this is going to be in the negative j hat direction, and this will be in the positive I hat direction.
Okay.
Because I've just defined the j hat to be this one instead of that one. So that's important because when I'm calculating the total force, I have the tension force. And then, so the tension force is going this way, but I want to calculate when I do like force equals mass times acceleration, it's net force, right? It's F net equals mass times acceleration.
Yeah.
So the net force, so there's the tension. They're asking us for, in this question, they want to know the tension. So to get the tension using the mass times the acceleration, we have to keep in mind that there's another force acting against it. So the net
Yeah.
force is going to be the tension plus the gravitational force that is perpendicular to the motion. So the force perpendicular to the motion is going to be the tension force minus this mg sine theta.
Okay.
So this is going to be minus mg sine theta. Is that okay?
Yeah.
And then this will equal mass times acceleration in the in that direction. So the component of the acceleration in the direction of the tension force, that is a perpendicular to the motion.
Okay. Perpendicular.
Yeah, so the acceleration, so we want the tension force. So to calculate the tension force, we're going to take the mass times the acceleration in the direction of the tension force.
All right.
And the acceleration in the direction of the tension force, that's like centripetal acceleration. So this is going to be the V squared over the radius of the circle. Do you remember the radius of the circle?
The radius of the circle would be, let me just look at this. Would it just be H?
Precisely. Yeah, because the rope is H, the rope's length is H, and we are traveling, we're traveling in a circular motion by the rope. The rope is creating a circle in the air. So I turned acceleration into V squared over H.
Okay.
Excellent. Okay, now we want to solve for T. So we have T equals M V squared over H plus mg sine of theta.
T, yeah.
Okay, and then we sub in the value. We already found out what V squared of theta is, right?
Yeah, it's 2gh sine theta.
2gh sine theta. This is all over h plus mg sine of theta. Now, what we notice here is we can cancel out these h's.
Yeah.
And then so this becomes, we have 2mg sine theta and mg sine theta. So the final tension will become,
I'm just writing everything down quickly. So it would it just be 3mg sine theta?
very good. Very good. Yeah, that's exactly what they got in the answer. Yeah, so in the answer they did that in like 2 lines, but I think it was useful to write it out in more lines.
Oh wow, it's already 8:50. We're only halfway done it. That's
Yeah,
a single question.
yeah, this was a very tough question. Yeah, I sent an email last night. I spent 2.5 hours doing parts 1 and 2 of this module 3. It's quite a lengthy one. I think
No.
part C is easier.
Yeah, and apparently, and you're only supposed to spend 45 minutes on a question.
That's what they said.
Yeah.
Only 45 minutes to explain it to the group.
Yeah, like you're not expected to finish the question entirely, but like but yeah, I think 45 minutes isn't enough to do most of these questions.
Yeah, I mean, for it to be enough, then everyone would have had to have looked at the problem thoroughly and already understood it completely. Because if I were explaining like these angles and stuff, I can't just say that this is theta without going through the steps for why that's theta.
Yeah. So, okay. So it seems like we will not be able to finish all 4 questions within like the 10 minutes now and the hour tomorrow. So maybe we should just choose a different, like for next time we should choose like a harder question just in case if we won't be able to finish everything in time.
Okay. Yeah. So choose a harder question.
Yeah.
Okay. Because this one you find a little bit too easy.
Well, like I just want like I just want to like get help on the hardest questions so that I'll be more prepared for the test.
Yeah. Okay. Yeah, so you can let me know which question you find the hardest, and then I can work on that one.
All right. Uh, yeah. Okay. Should we just go to do as much as part C as possible?
Okay, sure. So for part C, it's asking at what critical angle theta is he forced to let go of the rope? So it says, if you're looking at the question right now, it says if the maximum force with which he can pull on the rope is equal to twice his normal weight, then at what angle theta is he forced to let go of the rope? So the maximum force, this T, when we're at the critical angle theta, the tension is going to be twice of his normal weight.
Okay.
Do you know what his normal weight is?
Okay, so weight is equal to just mg.
Yeah, so twice the normal weight is 2
Yeah.
times mg. And then we have another formula for the tension of the at the critical angle. We already calculated just now that tension is equal to 3 mg sine theta, right?
Yeah.
So this equals 3 mg sine theta, theta critical, because we're subbing in theta critical here. So now we have, we can cancel out these mg's. Mg is gone. And we're left with just 2 over 3 equals sine of theta critical.
Yeah.
So theta critical equals 41.8 degrees. That's by plugging this into a calculator.
All right.
And then the next part of this question was, what is the velocity, the critical speed at that point? So we already have a formula for the velocity as a function of theta. That was square root of 2gh sine of theta. And in this case, it's sine of theta c. So now we could, I suppose, plug in 41.8 degrees into there, but instead of doing that, we know that sine of theta c equals 2 over 3. So instead of plugging in 41 degrees, we can just plug in the sine of theta, this whole thing equals 2 over 3.
I see.
And so that's why they were able to get 4 over 3 GH.
So it would be 2gh times 2 over 3.
And
Okay.
that's 4 over 3 GH. So part C, I think, as long as you're okay with that, then part C is done.
All right.
And for part D, let me try to, do you want me to go a bit faster?
Yeah, I don't think we'll have enough time to start the next question.
Okay, so let me just at least try to get through this question then. So now he lets go of the rope. So he was carrying the rope all the way up to here, and then he lets go of the rope because there's not enough tension to support him anymore. And then he undergoes this parabolic motion until he hits the water. So now it says use conservation of energy to calculate the speed when he hits the water, VF, the speed when he hits the water. So we have again, E total equals delta K plus delta U. And this has to equal 0. And we now have the delta K, that's going to be half m v final squared minus v initial squared. V initial squared is 0. And then we have mg h final minus h initial. And this time, so this time the initial is 0, and the initial height is h, right? That's where he started. But the final height is going to be 0 because now he is fallen in the water. So this is 0, right?
Yeah.
Okay, so now we have half
Wait.
and yeah.
Okay. Oh, yeah, I'm trying to realize that doing that, making the initial point the point of him letting go is kind of a bad idea. Yeah, I
Yeah,
don't know why I
because
thought that was a good idea.
no, it was a good idea, but the thing is that then you would have to add all of the, so then your initial point would be
Yeah, it would be like you would have to include the square root of 2gh sine theta, and then that's going to be very annoying.
yeah, in that case you would have vertical, you would have some potential energy at the beginning. I mean, you would have a different amount of, you wouldn't have this much potential energy, you would have less potential energy. So but then, yeah, your kinetic energy over there is different, right? That's what you're saying?
Yeah.
So if you start from here, then your kinetic energy would be, here I'm able to say the initial kinetic energy is 0 because I started from there. If instead you want to start from here, yeah, you could say that the initial kinetic energy was that complicated expression. So we could have done it that way too, but I just chose it to do this way so that I have more zeros.
Yeah, I whatever. It's okay. It's okay. Continuing on.
So they want us to find, so the total change in energy is 0, and they want us to solve for VF. They want us to get the VF. So here we can put the MGH on the other side, and we just do a square root, right? I think you're very good at the math, so this type of stuff you don't even need me for. This
Yeah.
2GH, right? Square root of 2GH. That's what they got in Richard Epps solutions too. And then they said, what is the angle alpha of his final velocity vector below the horizontal? So here's the horizontal.
Oh, sorry, because I just didn't write everything out yet. I just need a second.
Yeah.
2GA's square root of 2GH. All right. All right. Yeah, I'm ready now.
Okay. Yeah. So now they want the angle that the the velocity vector at the very end. This is the velocity vector, the final velocity vector. What angle does that make with the horizontal?
Let's see. So the final. Oh. Okay. So we have it. We have the final one. I guess.
Yeah, we have the final. Yeah, that's just the alarm saying that it's 9 o'clock. Okay, but I can try to finish this one. So yeah, we have the VF. So VF equals square root of 2GH. That's true. And we want to get the angle theta. And we only know one length. So we want to get this angle and we only know one of the lengths.
Oh. Would we use? I'm trying to think of sine or cos law, but I don't know if that's good. No, that's, well, I have one angle and one length. And we're trying to find the angle and we only have one length.
Yeah, so basically you can't do it, right?
Yeah, not that I could think of.
Okay, so because we can't do it, we're going to go back. We have this VC. We have that VC equals square root of 4/3 GH from here.
Yeah. Yeah.
And when the daredevil falls, his velocity here is VC, right?
Yeah.
And in terms of his final horizontal velocity, none of it is coming from gravity. So I'm going to write this down because I worry that if I don't say it, then you might get lost when you're trying to read these notes. So VFX must be the x component of VC, because
Oh yeah, because there's no acceleration in the x direction.
yeah, so because G only acts in the y direction.
Yeah, there's no x acceleration, so it has to be this. Yeah.
So we're going to say that VFX equals VF, this is going to be equal to VCX. Oops, draw. So
All right.
this is VCX. So now we have two, so we can get, I also put theta instead of, I wanted to put alpha. So we now have two lengths and we want to get the alpha. But to get the alpha, yeah, so one thing we could do is we could get VCY, and then we do tan of the tangent of alpha equals VCY over VCX. Sorry, I'm rushing and I'm making mistakes now. So this is VFY. Yeah, I think I wrote that out right.
Yeah, but yeah.
VFY. Does that make a bit of sense?
Yeah.
Yeah, okay. So we want the tangent of this. So if we can get this ratio, then we just have to do the arctan of that ratio and we get alpha.
All right. Okay, so to do that, okay, I don't know how to get there.
Yeah, okay. So let's do, so we have that VFX equals VCX. You figured that out yourself as well because there's no horizontal velocity from gravity. So all of the final velocity in the x direction will come from the previous horizontal motion that he had.
Yeah.
And then I'm just going to draw another angle here. So I'm going to say this is the angle between the horizontal and the rope at the time when he lets go of the rope. So this is BC. And the rope is always horizontal to his motion. I mean, sorry, perpendicular to his motion.
All right.
And then we have components of this vector. So we have components of that vector. Let me get the red. Okay, so.
Oh yeah, and we figured out theta is at the top there. Yeah,
yeah. So then this, we want VCX, right? So this will be VCX. And that equals.
Yeah, it would be VC sine theta.
Very good. Very good. So then we have that VFX equals VCX equals VC sine theta C. And we know what sine theta C is, right?
Yeah.
We got that from just a couple slides ago.
Yeah.
Yeah, so sine theta c is 2/3. So that's what, this is 2/3. So we have this, okay. So great, we have this. And then we also know VC. We got VC, we calculated that. We got VC equals square root of 4/3 GH. So this is the square root of 4/3 GH times 2/3.
Okay.
Okay, and then is that okay if I leave it like that, or you want to say?
Yeah, I just need a second. And yeah, we found VC. Root 4/3 GH times 2/3. Yeah, and then it's VFY over all of that.
VFY over all of that. So that's VCX. And to get, yeah, so VFY, to get VFY, we use the Pythagorean theorem.
Yeah.
So the Pythagorean theorem, so here we have VCX equals VFX, and then we have VC or VFY. VFY, and then we have here we have VF.
Yeah.
So we can get VFY equals the square root of VF squared minus VFX squared.
That would be, so the square root of the square root.
Well, you don't have the square root of the square root. You have the square root of the square root squared. So we have VF.
Oh yeah, squared.
Yeah, so you remove the square root there, right? So
Yeah, you're right. You're right.
2GH.
So yeah, just 2GH minus the 4GH 4/3 GH and then 2/3 squared.
2/3 squared. Okay. So we can do this together. So 2GH minus, then we have 4 and 4, that's 16. Then we have 9 and 3, that's 27.
Yeah.
So then to get a common denominator, we'll do 54/27 GH minus 16/27 GH.
All right.
And this will just be, I think, 38/27 GH.
All right.
And then we do the tangent. So, okay, we've got tan of alpha equals VFY over VFX. And that equals, so that's going to be the square root of 38/27 GH divided by the the VFX. So that was the 4/3 square root of GH/3.
Yeah.
So then that's going to be, we have square root of GH and we have square root of GH. So square root of GH and square root of GH, those are both gone.
Yeah, you're right.
And then what we end up with is square root of 38/27 divided by 4/3 times square root of 3.
Yeah, so we would have. Yeah, and then at this rate, it's just like,
Yeah. So
yeah, I think I don't know if there's too much point going any like more simplified when it comes to all of this because it's just radicals, square roots at this point.
yeah, so the 9 times 3 is the same as 27. So this will cancel out with that.
Oh, I see.
And then, so we just end up with this equals square root of 38/16. And that, so then that basically just means alpha equals 57 degrees.
All right.
So that's what they got in the solution as well. They did
All
it
right.
in like 2 steps in the solution. But
2 steps.
did you see the solution?
Yeah, that's a bit crazy. Okay, yeah, I don't want to keep you waiting any longer. So yeah, thank you so much for helping me.
Yeah, no problem. Yeah, unfortunately, this was a long question. I think there was a lot going on. Do you feel comfortable? You understand everything?
Yeah, yeah. I guess the most confusing part was D here with finding the angle
Yeah.
through like equaling it, like making the components equal to past parts like that. I wouldn't have thought of.
But I think you did think of it in the end, because then when I started writing Vx must be Vcx because G only acts in the y direction, then I think you completed my sentence. I was halfway done writing this and then you figured it out yourself.
Yeah, the problem was like starting that thought.
Yeah.
I
Yeah.
tend to feel like, oh, I can't do this, and
Yeah. I think it's got to take a long time to figure, because you have to think about it. You have to be like, okay, how am I going to get those components? I only have one length and one angle. So how am I going to get the angle if I only have one length? Then basically you have to figure out either VCX or VFY. And then, or you have to figure out VFX or VXY, VFX or VFY. And then VFX, it happens to be your horizontal motion at the end has to be equal to the horizontal motion when you first let go of the rope, because the only force acting on you is gravity, and gravity isn't doing anything horizontally.
I see. All right. Thank you very much for helping me, and I guess I will see you tomorrow.
Yeah, so is there a question you want to do I prepared the part 2 of this long answer module 3. So the blocks where there's 2 pulleys.
Okay, so part 2. Part 2.
And I think that one would be possible within an hour because it's shorter. Um, that one is 5 parts, but the first part is very easy. It's just mechanical energy, mechanical advantage equals 2.
All right. I'm just quickly looking over all of them. The third one is spring. The fourth one doesn't even have a graph. Doesn't even have an illustration. Car. How about let's just go straight to 4, and if we have time, we could do 2 and possibly 3 if we really get things done quickly.
In 1 hour, you want to do 4, 3, and 2?
Well, like start with 4, and depending on how much time we have left, try to attempt one or both of the other questions.
Okay, so 4 is the one you think is the hardest?
Yeah, like I tend to see that like the last question is the hardest one,
Okay,
which is
so yeah, so
which isn't.
tomorrow it's going to be from 2 to 3 p.m.
Yep.
Okay, now I'm going to have to prepare. So I wrote out a solution for part 2, which is the one with the 2 pulleys. And so I'm ready to do that one. But for the fourth one, I don't know if I'll be able to look over that one between tomorrow morning and 2 p.m.
Okay, if you don't if you don't finish that in time, we could start with number 2.
Okay, maybe we can start with number 2 because I know, like, I did that one last night. I spent an hour reviewing it and everything, and then if we finish that early, then we can start doing the question 4.
All right, I will see you then.
Okay, sounds good.
Goodbye.
Okay, goodbye.